start. Okay. Did I usually have to change the screen resolution in this? Yeah, so I didn't have to do it today. It just start up correctly. Because I just noticed that it's not the same sequence that I usually do it. All right, so what we'll do today is we're going to focus on structures today. Yes? I believe so. Yep, I am recording. Streaming, actually. Okay, so we'll go ahead and start with structures. Even though we are using structures, this is not beyond the scope of cisp310. So if you have taken cisp310, this stuff should look, I would say, somewhat familiar. They may or may not use structures the way that I'm going to use it here, but it should not be too different either. Okay, so we have a structure X here. X, uppercase X, is the name of the structure itself. The word struct, S-T-R-U-C-T, is really analogous to class, except every member of a structure is public. And in C, plain C, not C++, a structure cannot have function members. So it cannot have methods. It can only have attributes or data as members. And you cannot control the scope. You cannot say, okay, this part is private, this part is protected. Everything has to be public. Okay, so other than that, it's kind of the same thing as a class, which means it is a cookie cutter. Okay, you use it to stamp out variables, objects, and whatnot. So we'll go ahead and say, okay, this part is a unsigned integer type. We'll call this one I, and we have another one called J. Okay, and then we have a pointer here, which is pointing to another structure X, and we'll call it next. Okay, so if you have taken CISP430, okay, some people have in this class, this is how you make a linked list. If you have not, okay, it's okay. Next is really a pointer pointing to a thing that is of the same type as a struct X. Is that okay? All right, cool. So now we can go ahead and, I'm not going to write any subroutines just yet. Okay, I'm just going to do everything in main, and then we'll try to figure out, how this is going to happen in assembly. So we'll do everything in main first. So we have struct X. We'll have two structures here. I will call the first one S1 and call the second one S2. So S1 and S2 are structures. They're not pointers to structures. They're actual structures. And then we have the usual return 0 here. And then we'll just do some manual initialization. So we'll say, I of S1 starts with the value of 4. J of S1 starts with the value of 6. Okay, these are just random values, by the way. I mean, there's no particular reason why I chose these particular values. S2.I start with the value of 1. And then J of S2 starts with the value of 3. And then the pointers, the next pointers are all nulls. Basically, they're zeros. So S1.next equals to S2.next equals to 0. How many people know that you can, quote unquote, chain assignment operators like that? Okay, very good. And the reason why you can chain assignment operators like that is because the value of an assignment operation is the right-hand side of the expression. So that's why this is equivalent. Okay, if you need to put in parentheses, this is equivalent to first performing this assignment, but because the value of the assignment operator is the right-hand side of the assignment, so that means the value of 0 becomes the value of the assignment operator itself, or the assignment expression. That whole thing is now 0, and that 0 is now treated as the right-hand side of the outer assignment expression. So that's why you can stack or chain assignment operations, which is really kind of cool. Is that okay? Now, because assignment operators naturally is right associative, so that means these parentheses are actually not needed, because when we have a chain like this, it will naturally perform the rightmost assignment first, and then the second rightmost, and so on. So that's basically all features of the C programming language. Are we good so far? Okay. So when I compile this program, okay, this is not a very exciting program. It doesn't do anything that is really too exciting, but it will serve as an example to illustrate concepts that I want to illustrate in today's class. So I'm going to save this, switch to a command line interface, and we'll start a new tab here. And then we'll compile the program. So struct.c is the name. So we have a gcc-g to include debug information, warn all, and then the name of the program, which is struct.c. It compiles, it complains that S1 is set, initialized, but it is not used. I don't understand why S2 does not get a complaint. Oh, I know why. Because of the chain of the assignment operation, which is actually, it has to do with how we analyze the whole thing, because that actually does not make use of the value of S2. It makes use of the value of the constant 0. But I guess the compiler considers it making use of S2. So anyway, that part is not important. So now we do a GDB. Okay, we put a breakpoint on line 13. Okay, we'll put a breakpoint on line 18. Run the program through. Okay, so continue. Now we are at the return statement. So when I print S1, it shows us that member I has a value of 4, member J has a value of 6, and the member next, which is the pointer, is a null pointer. Are we really surprised? No. Okay, this is nothing to be surprised. Okay, so what I want to do now is to say, where is S1? What is the address of S1? Okay, now obviously we cannot tell right now, because this is an internal address that only the program knows, because that's determined at runtime. So now we can see that, okay, S1 has an address of blah 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 blah, and we'll just refer to the last 3 digits here, because the rest is going to be the same for all the addresses that we are interested in. So in this case, this particular address ends with 1E0. Okay. Let me ask you this question. What do you think is the address of, now these parentheses are not needed, but I'm putting it here just to emphasize what I'm trying to do. I'm trying to find the address of member I of the structure S1. What do you think that address is? Now, I don't really care about the type. I understand the type is different, because the address of S1 is a pointer to a structure, and then the address of member I of S1 is a pointer to an unsigned char. Okay? So I understand the type is different. I only want to know where it is. What do you think? Member I is the first member. Yep. Why would it be less? Because this address, 1E0, is pointing to the beginning of the entire structure already. If it has to move, it's going to move up, correct. But the question is, does it even have to move up? I know where to find a book. Now I'm trying to find the cover page of that book. Where is the cover page of the book relative to the position of the book itself? It's the same as the book itself. Okay? In other words, I'm expecting this to print exactly the same location, 1E0. Is that okay? Well, let's check. Well, it is indeed 1E0. Okay? But let's kind of pause here and make sure that I want to make sure that it makes sense to you. A structure is nothing more than what we call an encapsulation of multiple items that is inside it. So it's more or less like an envelope. Okay, you're putting multiple pieces of paper into an envelope, and then sometimes we can treat the entire envelope as one thing. We can pass it around. Other times we want to look into the envelope and go like, okay, I just need the first piece of paper in the envelope. So we need to access the individual members. So if I can say that the entire envelope, the entire package, is at location 1E0, and now I'm interested in the address or where I can find the first item of the entire structure, does it make sense that they are the same address? Mm-hmm.
Is the first thing always the same address as the structure, the start of the structure itself, or is it different?
It is conventional that they are the same. Now, whether the compiler or the C programming language actually has a clause to say that it has to be the same, that I do not know. I have not read into the NCC standard for this particular purpose. But all the compilers that I know of, would kind of assign addresses of members according to their order in the structure. Okay? So I could be wrong that some compilers may not play by these rules, but that's the usual convention because it makes sense. Yeah. Mm-hmm. Okay, so if I were to print out member J here, where do you think member J is going to be located? Member I is a 1 byte unsigned integer. Where do you think J is going to be? The next byte, right? Seems to make sense. So we are expecting this to print 1E1. Okay, so we'll check that. Oh, okay, indeed, it is 1E1. Cool. All right, so now we have the third member. The third member is next, right? But next is not a 1 byte thing, because next is a pointer to something. Any pointer in a 64-bit architecture is going to take up 8 bytes or 64 bits. Is that okay? Do you think that has anything to do with where it starts? Because the address needing 8 bytes is only affecting how long it is, but would it have any impact on where it starts within the structure? It should not, right? Okay. So we'll go ahead and take a look at that one. And it does. Do you guys see how we went from 1E0 for the first member to 1E1 for the second member? The next byte that is available is 1E2 because member J is only a 1 byte thing, so it takes up the byte at location 1E1, so 1E2 is the next available location. So why are we skipping 6 bytes here and go all the way to 1E8 so that we can find the address at 1E8 instead of 1E2? Do you guys see what I'm talking about? We're wasting 6 bytes for some reason. Now, yeah. Exactly. It is keeping everything, quote unquote, aligned with the width of the data bus. Okay, I'm hoping you guys still remember the width of the data bus, like your RAM. The D port has its own width, right? So in the toy processor, it's only 8-bit wide because we keep everything just byte wide. With the processor that I have in this particular laptop computer, it's a 64-bit processor running in 64-bit mode. Okay, which means every time I go to memory, I actually get 8 bytes back. Every single read operation is reading back 8 bytes. Every single write operation is updating 8 bytes. Is that okay? So that means if I just need to access member I of S1, it's getting 8 bytes back. I'm just ignoring the other 7, the 7 that I do not need. If I want to access J of S1, I'm reading in the same 8 bytes, ignoring the 7 bytes that I'm not interested in, and only keeping the one that I'm interested in, and put it into an 8-bit register or something like that. Is that okay? Why does that have anything to do with wasting 6 bytes here so that the address is starting with so that the address member next is starting with a location that is divisible by 8? What if it is not? So the question is, what if it is not? Okay, so let me see if I can kind of use a text document to display this. I think I can do this. So we'll see whether this works or not. Okay. So I would use the same convention as before. So let's say this is not wasting space. Okay, so not wasting space. And I'm just going to use the letter N to represent a byte that is used for next as a member, the letter I for a byte that is used for the member I, and the letter J for a byte that is used for member J. Okay? And I'm still using the same convention. If it is higher up, it is representing higher address. If it's lower, it is lower address. Okay? So this is, I'm describing the higher 8 bytes at this point. So if I'm not wasting space, then I would have 2 bytes that are not really used for anything. The other, oh no, I take it back. So I have 6 bytes that I'm not using for anything else, and then the least significant 2 bytes here would be the most significant parts of the next pointer. Okay, and then the lower byte is going to have the 6 bytes here representing the next field, and then we have a J here, and then we have an I here. I know this looks kind of backwards. Do you guys want me to kind of flip it the other way around? I is, okay, this I here is the least significant byte. This J is the second least significant byte. And then the N's are the most significant 6 bytes of this particular 64-bit thing. Okay? And then on the next 64-bit word, these 2 N's are the 2 bytes that still belong to the next pointer. It's the most significant portion of the next pointer. These 6 bytes are actually not used. Is that okay? The idea is N, or the next member, is now split into 2 different 8-byte words. Now, whenever I perform a memory read, I can only read this entire thing, or I can read this entire thing. So that means if I need to retrieve the pointer that we call next, I now need 2 read operations instead of 1. Is that making any sense? That is the reason why we waste 6 bytes, so that N is by itself in the upper portion. So that's why we are going to do this. So I'm contrasting these two. Wasting space, but improving performance. So the alternative is to say, okay, we're going to use an entire 64-bit word for the member next. And then for this particular 64-bit word, I'm going to waste 6 bytes out of 8 and only use J and I as the least significant 2 bytes. Is that making any sense? In the end, I'm still using 2 64-bit words, either way. But with the second method, I get the performance gain. With the first method, I'm not getting the performance gain. Now, somebody can argue and go like, but in the first method, all these question marks can be used for something else. You're absolutely right. Those question marks can be used for something else. But if that something else is also an 8-byte Y thing, that means accessing that thing is going to take up more time than it needs to anyway. So we are now starting to kind of push the misalignment to more things, and therefore the performance is going to lower even further. Is that making any sense? Yep.
If we were to add another element to the structure, like let's say K.
But the question now is, where are you going to add K?
Well, that's what I'm asking. Or just after next.
Okay.
After the next pointer.
That's a good question. I can see where you're going. So let's go back to the program and check that out. Okay, so we go back to struct.c, and we are adding it over here. It's just 1 byte. It is called K. Okay. So now the question is, are we going to be stingy and say, oh, we got 6 bytes that were wasted earlier. Now we can just put K along with IJ so that we are only wasting 5 bytes out of those 8, and then we will keep next on its own 8-byte word, so we can maintain performance, and we are not going to waste another 8-byte word. Okay, so that's a very good question. What do you think? What do you guys think is going to happen here? I don't really have the answer, so I'm really asking the question. I'm taking bets.
I think it's going to waste more space just above next.
Okay, so you're thinking that the address of k is going to be above next, and it's just going to take up the entire 8-byte word.
Yeah.
Okay, that would be my assumption too, because otherwise the compiler will have to be very smart to kind of backfill spaces that it can backfill, and that just doesn't sound right to me, because I used to write compilers or maintain compilers, and it's not worth the trouble to do this sort of thing. Okay, so let's try it out. What do you think? How about the rest of the class? Do you guys have any personal prediction? No? If you are to write a compiler, would you spend extra time and extra code to optimize the use of space in situations like this? That is the question. Okay, so most people are saying no. Okay, so we'll see. We'll see whether GCC by default is going to do this or not, because I really don't know. This is new to me. I like these questions where I do not have answers to. There we go. Okay, so what we're going to do is we'll print it first, okay, which is not indicative of actually how memory is used, because GDB can be just okay, I'm just going to follow through according to the order of the member. It's just listing it according to the order. So this may or may not actually be indicative of the memory locations. Okay, so now we start to print the addresses of all these things. So we say, where is I? Okay, 1D0. Where's J? I'm suspecting that would be 1D1. Okay, just like last time. Okay, no surprises here. So K is the suspicious one, right? Because according to, if the compiler is really trying to try to make the best use of memory locations, then we would suspect that K should be 1D2. On the other hand, if the compiler is not doing any optimizations like that and just go by the ordering of things, then it will go to 1. It will go to 1E0. It will go to 1E0 because next is going to start at 1D8, but because it's 8-byte wide, it will take up 1D8 all the way to 1DF. So that means K, which is following next, has to start with 1E0. So it's either 1E0 or 1D2. So what's your bet? I need to write an app so I can support in-class betting. Okay, well, I really don't know the answer. And it is 1E0. It's just going to waste even more space. So it doesn't go back and say, oh, we just wasted 6 bytes and we can go back and use one of those 6 bytes. Nope, it's just going through the sequential order. That's interesting. What about this? Size of struct X. Now, by the way, what is size of? Okay, let me give you 3 options. Is it a macro? Is it a function? Or is it an operator? That is correct. Size of is actually considered an operator. Okay? And it tells you the number of bytes used by whatever is in parentheses. Now, what can you put into the parentheses? You can put in a type just like that. Or you can put in int. You can put in uint64_t. Or you can put in a variable. For instance, I can put in S1. I can put in S2. I can put in S1.I. I can put in the address of S1. So it can be an actual thing. It can also be just a type. But it will tell you how many bytes that thing is going to take. So what do you think this is going to print? How many bytes is a single structure, struct X, going to take? The first 8 bytes will be used by I and J, and then the 6, we'll have 6 bytes basically wasted within the first 8 bytes. The second 8 byte is next all by itself. And should I count just one more byte for k? Or is it going to use up all 8 bytes on the last 8-byte word? It's going to use up all. So I'm suspecting this is going to print 24. And that it is. So it really is quite wasteful if you think about it. That's why we need 16 gigs and 32 gigs of RAM these days. There is, by the way, there's an option of compilers. So you can actually make a compiler optimized for size versus speed. The default is to optimize for speed, but you can actually turn on the option to optimize for size for structures. Then it will try to bin pack everything to use as little space as possible. But it will be at the price of performance. Okay? Yep.
How much performance is sacrificed?
You are looking at 2 memory access instead of 1 when you're accessing next in this case. So then the actual hit of performance depends on how frequently are you going to refer to next. Every time you update to next, it would take twice as many memory operations. Every time you read next, it's going to take twice as much time as the more optimized version. So the actual hit of your program's performance depends on how frequently are you going to make use of the member called next. Any other questions? No other questions? Yep.
Is this going to go in the tunnel?
Maybe. I haven't decided. How about this? No, that's the default answer. Unless otherwise noted. But seriously, do we have any questions about this part? No questions? Okay. How big is a pointer in the toy processor? In other words, when you are dereferencing a register to go to a memory location to update the content of the location, what is the width of a pointer with a toy processor?
1 byte?
Sorry? 1 byte. Yes, 1 byte wide or 8-bit wide. So in the toy processor, we wouldn't be wasting space like this because everything is only 1 byte wide. Okay? So that kind of helps in terms of saving space. So do we have any further questions about this? No? Okay, well, shall we try to write the same code in TTP ASM, in the toy processor assembly? Okay? Okay, so we'll start with that, okay? The other class was a little bit more brutal. I kind of started off with passing the address of the members of the structure to swap so that I can exchange the values of the members of the structure without actually, going through this part first. So that was a little bit more brutal. This is a little bit smoother as a transition. All right, so let's go ahead and I'm going to take out all of these except for this one. The other ones are, I suppose I can keep this one here. That we can remove. That we can remove. I have to be careful not to exit the entire thing because otherwise it will just close everything. There we go. All right. So we'll just go to this is our program in C, and then we'll try to write this code in assembly. So this is not yet about calling subroutines. It is really just about how do we allocate memory for local variables that are structures, and once it is allocated, how do we access individual members of a structure in assembly? So that's basically what we are dealing with here. Now, unfortunately, in all assembly language, there's no such concept as a structure. In other words, the whole concept of a structure is a high-level language concept only in C and C++ and other programming languages. In assembly, it has no such concept. So in order to remember, the ordering of the members and where they are supposed to be from the beginning of a structure, I'm just going to use comments to remind myself where those things are. Okay. So over here, I'm just going to write in comments, okay, and I'm just going to describe description of struct X. This is really just comments, okay. Remember, slash slash is the beginning of comments. It is not really a part of the program. Offset of member I from the beginning of a structure is 0 bytes. Okay, we observed that a while back. Offset of member J from the structure, from the beginning of the entire structure is 1. And then offset of next from the beginning of the whole structure is 2 in this case, because we don't have to waste bytes, because everything is byte aligned anyway in the toy processor. And then the last one is K. Offset of member K from the beginning of a whole structure is 3. And then one last thing I need here is to remember the size of, in this case, a struct X is only 4 in this case. So I'm writing all this down because in assembly there's no way to actually express a structure. So a structure can only be implicitly expressed by looking at certain offsets of the beginning of a structure. So are we doing okay so far with this? Okay. No actual code, it's just comments to remind myself where do I find each member of a struct X. All right, so with this part done, I'm going to write the main subroutine. So in the main subroutine, we're going to say subdd, okay, that's the usual thing of initializing the stack pointer, okay, turn it into 0. And then main is the entry point of main. It is not necessary, but I'd like to put it here so that we're pretending that main is actually a function, but it's not. Okay, so the first thing we need to do in main, according to the C code, is we are going to allocate space for 2 local variables. One is S1 and one is S2. What do we need to do? Not to think about this in terms of assembly instructions, but think about conceptually what do we need to do to the stack pointer to allocate space for local variable S1 and local variable S2. What do we need to do to the stack pointer? Sorry? We do the decrement. How much do we need to decrease? 4 for the first one and 4 for the second one, so for a total of 8. Okay? So in actual code, so what I'm going to do here is I'm going to draw the picture of what the stack should look like after we allocate for the local variables. Okay? So what the stack is going to look like using the convention of upper is higher memory location and down is lower memory addresses. So what the stack would look like after the allocation is done is S2.k is going to be here at the highest location. S2.next is going to be here. S2.j, and then we have F2.i, and then we move on to the S1. Now this part is really just a convention. Variables that you declare first from left to right usually has a lower address. Now, once again, it is just a convention. A compiler can decide not to play by those rules. Okay, so I'm using the same convention here. So S1.next, S1.j, and then S1.i. There we go. IJ next K, huh? Oh, S1, that's right. Okay, there we go. Thank you. So the entire S1 is using these 4 bytes. The entire S2 is using these 4 bytes. And the allocation means the stack pointer would end up pointing here because the stack pointer always points to the last thing that we either push or reserve on the stack. Is that okay? All right, so what do I do to adjust the stack pointer so that it goes here? Yep.
I thought that S1I was the first thing that we pushed.
It has the lowest address.
Yeah.
So it's the last thing that we push. Because remember, when you're pushing, the stack pointer goes down when you push items. So the last thing that you push or the last thing that you reserve is the thing that has the lowest memory address. It's counterintuitive, but it works out better that way. So are we good so far? I can do this by 8 decrement D. Or this time it makes sense to do a LDI A8 and then just do a subtract, right? Okay. So we can do that. LDI 8, A8. Okay, there we go. And then we subtract A from D to reserve for both S1 and S2. Is that okay? So when you look at the instructions, when you look at line 17 and 18, there's really no telling why I am subtracting 8 bytes from the stack pointer. Okay? And that's why commenting is so important when you write code like this in assembly, because otherwise you have no idea why I'm reserving 8 bytes. What are these 8 bytes used for? Okay? Unless you comment like this, there's no way to actually remember what it is used for. Yep.
In the C code, I don't see the cake anywhere. I don't know if you took it out by mistake.
Oh. That's because I made that change in VI and it didn't make it here. Sorry about that. There we go. Yep.
Would it be a bad idea to just do load ID and then the absolute offset to where it would need to be to have space for all that? Isn't it just like an absolute number since it's at the very start of the program?
Absolute number.
So you take 255 or whatever, the very last spot in RAM.
Oh, I see. So instead of doing a sub DD, you can just initialize and go LDI D comma. So that would be 0 minus 8 or 256 minus 8, which is 248. So you could do that, but that would not demonstrate how we will generally do it in a subroutine. This way, this is exactly, if this is not main, okay, if this is a subroutine called sub1, I would be doing exactly the same thing. Because these are local variables, and this is how we allocate from the stack when we have local variables. Everything is just relative to where the stack pointer is at the entry point of the subroutine. So that's why I chose to do it this way instead of just initializing the stack pointer to the right place to begin with, because that would not illustrate what you need to do when you're in an actual subroutine.
So that would really only be like okay in main, but not anywhere else.
Correct. And that's only because in this toy processor, we don't have anything to return to, so main is technically not really a function. Yep.
So does the compiler have a method to determine like that the struct has 4 bytes and you have 2 structs, so it needs 8 to subtract 8 for load 8?
Yep, it does. All right, cool. So now we're done with line 13. Now we move on to line 14. Okay, line 14 says, the I member of S1 needs to have a value of 4. Okay, we know that we're gonna have to do something like that. Okay, there's no other way to put a constant that is non-zero into something. Okay, so that part needs to be done. What about the other part? What do we need to do to get S1.I to become the left-hand side? Do we have anything pointing to it right now? Yeah, it just so happens that the stack pointer is still pointing at it, okay? So with this one, we can do a little shortcut and just say SDDA, and now we're done with this instruction, or this line of C code. Si.I equals 4, done, okay. The next line says, S1.J needs to be 6. Hey, that's just the next byte. I can just increment D and get there. Well, you don't want to do it in general, okay? But the toy processor, it wouldn't make any difference. But in an actual C program, in an actual architecture, especially a small architecture like the Arduino, it would make a difference. Because the moment you change your stack pointer, you're basically telling the interrupt surface routine anywhere below where I point to is available. So you don't want to change the stack pointer until it is no longer needed. Do we still need s1.i? Yep. So don't change it. So that means the only way you can get to it is to make a copy of the stack pointer and then increment the stack pointer on increment register C in order for C to point to s1.j. So I'm going to comment these two, just so that when you watch the video, even if you watch it in silence, it will give you some idea of what it is. So C is the address of s1.i at this point, and then after the increment, C is now the address of s1.j. Is that okay? All right. So now we do another store. Oh, before we store, we have to change A to something else. So we will change A to 6 because that's the value we want to store into member J of S1. So we increment C already, so we can just do a store CA at this point. All right, done. The next one is member I of S2 needs to get a value of 1. So C is now pointing here. We need to skip 2 bytes to get to S2.i. So incrementing by 2, increment C will be fine. So I'm going to comment this too. C is now the address of S1.next. C is now the address of S1.k. Oh, I missed one. We need one more. Increment C. C is now finally the address of S2.i. There we go. So that means now we can do LDIA with 1 STCA. Do you see how boring this is? And then the next one is going to be just 1 byte on top of that. So that's easy. Increment C again. C is now the address of S2.j, LDIA3, STCA. All right, so we are done with line 14 to line 17 of the C code. Now we're moving on to line 18. Okay, more boredom, right? Same approach. Okay, use C to compute where we are supposed to go. So, but this time, you can basically say, okay, let's do the whole thing all over again. In other words, you can always rely on where the stack pointer is. Okay, so you can always just reinitialize C, so you can redo the whole computation. And then the right-hand side is easy. The right-hand side, I can just initialize B to 0 because we are putting a 0 into both of the next members. So we can now focus on C and do some calculations on C. So we can get to, according to the C code, S2.next should get a 0 first. Okay, I know it doesn't really matter which one gets it first, but we want to preserve the C code as much as possible. So we look back at the map of the memory allocation. So let's see here. We just kind of scroll up a little bit. We want to get to this guy first. So how far away is it from where D is pointing to? So we have 0, 1, 2, 3, 4, 5, 6. 6 is correct. So we'll do it like that. Okay, so we say LDI A with 6. Add that to register C, because C was the same as D. Now it is D plus 6, basically. So at this point, C equals to the address of S2.next. And B is already 0, so we can do STCB. So this will complete S2.next equals to 0. And then the next thing we need to do is to get back to S1.next. Now we know the size of each structure is 4 bytes, so we can just kind of subtract 4 from what C has already at this point and get to it. So we can now do LDI A4, subtract that much from C. Okay, and I'll just write some comments here. C is now the address of s1.next. And we can do the store at this point, which will complete s1.next equals to 0. And now we are done with line 18. We are now ready to perform the return, which means we are now ready to deallocate all the local variables. That will just be involving LDA 8 with 8. And we want to add this time to the stack pointer. So this is deallocating S1 and S2 at the same time. And then depending on how you want to do it, because there is a return 0 here, so I guess technically speaking, we have to put 0 into A, and then put a halt instruction here. There we go. So the assembly code took 44 lines. And then the C code, technically speaking, is only from line 11 to line 20. Where's the, yeah, go ahead.
I'm curious, so in our C code,
Mm-hmm.
we have S2 being initialized with 0, but then S1.next initialized with the value of S2.next.
Okay, so when you look at assignment as operators, the priority of operators is going to do it like this. So the value of the entire expression in parentheses is the same as the value of the right-hand side of that particular assignment operator. So that means that's a 0. The entire thing in parentheses, this expression has a value of 0. It has a side effect of updating the next member of S2, but the value of the expression is 0. And that's the value that we are using as the right-hand side for this particular assignment operator. Is that okay?
Makes sense, yeah.
Yep. Because I think some people do not understand that they can actually do this. And you cannot do this in most other programming languages. Because in most other programming languages, assignment is not an operator, it is a statement. So with each assignment statement, you can only change one thing. You can only have one left-hand side to be updated. But in C and C++, and most languages derived from C and C++, assignment is an operator, not a statement. So the operator can go anywhere where an integer or some scalar type is expected. And therefore, we have that issue of, you can say if xyz equals 0, that is actually syntactically correct, because the assignment operation does give you a value of whatever the right-hand side is. So now the biggest question is, did you actually mean the assignment operation, or did you mean to compare whether xyz is 0 or not? That becomes the big question. If you turn on warn all in GCC, it gives you a warning. If you just say, if xyz equals 0, blah, 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 it gives you a warning, go like, are you sure, or did you mean to compare? So that's a nice feature. Make sure that you turn on warn all when you're compiling your C and C++ code, so that if you make that mistake using a single equal when you intend to use a double equal, the compiler can give you a warning, go like, hey, are you really sure? How many people have tried to intentionally use assignment inside a condition of either a while loop or conditional statement? It's very handy sometimes. It's just that you have to watch out when you do not intend to do that. Okay, so the program is done. The assembly code is like this. Let's run it and see what happens, because we can actually look at the RAM portion and see whether it has the content that we expect in memory. So we're going to copy, Control A, select all, and then copy, and then we go to our assembler. Go to source. Okay. Okay, somehow scroll doesn't work with this mouse. Paste. And then we just have to make sure that we don't have anything left behind here that is not needed. It's faster for me to just scroll like that. Okay, so we do have some extra stuff after the end. I'll just delete it. Okay, that's it. Yep.
Do we need to worry about creating the subroutine or the structure subroutine?
There's no subroutine here. Everything is in main.
No, in this one, yes. I mean, so to replicate the function from C onto your processor,
Mm-hmm.
would you need to worry about making the structure subroutine? It would just be fine.
Okay, let me see if I'm interpreting your question correctly. So you're referring to the definition of struct X. You're referring to this part? That part has no equivalence in the assembly code.
Oh, okay, so we wouldn't be able to.
Yeah. So this part is basically you telling the compiler, you telling the C compiler that a struct X has 4 members, and then the sequencing of the members is I, J, next, and K, and then the types are respectively, 8-bit unsigned, 8-bit unsigned, a pointer, and an 8-bit unsigned. So you're really just telling the compiler all that stuff, but then the compiler is responsible to generate the offset from the beginning of the structure to each member, and it keeps track of all that stuff internally. So you don't have to know that. The compiler is doing it all for you, and that's the nice value, the nice part of writing programs in C and C++, is the compiler tracks all that stuff. But when you're writing in assembly language, no assembly language that I know of has a construct to deal with structures. So that's why you kind of have to remember the offsets on your own. Yep.
So in this class, we're basically compilers. We're basically the compilers.
Well, yes, for the second half of the semester, that's basically what you're doing.
Okay.
But because of that, now you gain a new level of understanding of what is going on when you are running and also compiling your C code, which gives you additional abilities to debug your C programs. Because remember, I gave you all those kind of weird problems. You're calling some function, it returns to another function. Yeah, so that sort of thing, cannot be explained until you know how the stack is utilized. Yep. All right, so now we go back to the spreadsheet. Go to the RAM file, and then we'll download it, put it into the Logisim, and run it and see what happens. So we go to download as CSV. I'll call this struct.csv. And then let's see, do I have a Logisim already open? Nope. Okay, that's okay. Oh, it's Java, not log. There we go. And then load the processor. Load the actual image, struct.csv. And if I'm not really confident about this program, I would do the trace and log and all kinds of stuff like that. So I'm not actually confident, but I'm just lazy, okay? I'm using a greedy algorithm. If I don't have to do something, I'm not gonna do it. Control K one more time, and then right click, go to edit content. And then we look at the content over here, and we ask ourselves, do we have the right content here for S1 and S2 initialized? So to do this, we need to at least have a way to refer back to the C code, which is what we'll do right here. Nope, that's the assembly code there. Okay, that's the C code. And we want to move this to the side so that we can see both the C code and the memory content at the same time. So you guys tell me, did we initialize the structures correctly? Looks right to me, 4, 6, in S1 and then 1, 3 in S2. the k member is actually not initialized. It just so happens to be 0 because when RAM is reset, everything is 0 to begin with. Okay? But those 2 bytes are actually not initialized. So we are referring to byte FF and this byte here, which is FB. Okay? So FB and FF are both zeros because they are uninitialized. This one is put here intentionally. That's next. This one is also here intentionally because that's also a next. Yep.
Is that why if you don't initialize your variables, you could get random stuff? You could get whatever's left over from last?
Correct. Now, if this is not main, okay, and this is some function, and the stack has already been used for something else, then the structure, when you allocate for the structure, you're just moving the stack pointer by 8 bytes below where it used to point to, right? So the structures will basically, quote unquote, inherit the values from before, and that's why your uninitialized, structures would have some, quote unquote, random values, but they're not truly random. They're basically remnants from the previous invocations of some other functions potentially. Yep.
We could run into that in logicin too, right? Like if we ran it once and it changed those addresses and you didn't do a full reset, you just hit the actual reset button.
Yep.
On the clock load.
Yep. Yep, that's right. So are we good so far? Do we know how to access individual members of a structure as a local variable? So what is the new concepts in this class so far? Okay, did I change the way we allocate for local variables? Did I change the way we use the stack? So the only new stuff that we have added at this point is how do we access individual members of a structure, and how do we calculate the size of a structure? Only those 2 things are new. Everything else are kind of the same old as before. So are we good so far? Okay. So the next thing we're going to do is we'll integrate, because I don't think I have disclosed the solution to the swap homework assignment for this class. I don't think so. So we'll do that first. Okay. And then we'll do some funky stuff with swap. That's why we're doing this. So I'm hoping we'll have enough time because I want to show common mistakes for this particular program. And I will make those mistakes in C first, okay? And I will fix those problems incorrectly. And I'll ask you guys, what's going to happen if I fix those mistakes incorrectly, even though it's syntactically correct, but it does not do what it is supposed to. So here we have the original way to define t, which is a local variable. But then I am copying the code incorrectly here. I'm just saying that t equals to ptr1 instead of the dereference of ptr1. And then I say ptr2 equals to ptr1. Oh, the other way around, sorry. ptr1 equals to ptr2. And then ptr2 equals to t. In other words, I'm leaving out all the dereferences. If I were to compile this program the way it is, what do you think is going to happen? No, it's not going to swap the parameters. The compiler is going to complain. I cannot even run this program. Why do you think the compiler is going to step in and go like, nope, this is not going to compile? Exactly, the types are different. Okay, when you have an assignment operation, the left-hand side and the right-hand side should have the same type. What happens when one side is 16-bit and the other side is 32-bit? The compiler doesn't complain about those. Well, that feature is called what? There's a name to describe the automatic type conversion or coercion. It's coercion because it's done automatically. Now, type casting is something that you specify. So when you say in parentheses, change this to 16-bit wide, that is typecasting. But when the compiler is doing it behind the scenes, it is called coercion. Now, coercion can only work across scalar types. It can coerce an integer into a float even, okay? Even that was going to work. but it cannot coerce a pointer into something that the pointer is supposed to point to. It cannot coerce a pointer of one type into a pointer of another type. That it cannot do. Coercion can only do certain things, but not everything that is a mismatch. In this case, we have a mismatch because ptr1 is a pointer to an uint 8 underscore t, and t is just a uint underscore t. So if I want to fix this problem, but not really understand what the subroutine is doing, what is the quickest way to fix this problem as far as compile time error is concerned? I'll give you a hint. It only involves one character. Where am I going to put that one extra character? That's right. That will fix the compile time error. But what is it going to do? It's not going to crash. It's not going to cause any memory corruption. Okay? Memory corruption typically happens when you have dereferencing or array indexing. That's when really bad stuff can happen. This is not going to cause that kind of bad stuff to happen. But what is it going to do? It's going to exchange the parameters themselves, right? No harm done to anyone else. But is it doing anything actually useful? Why not? What happens to the parameters when the subroutine returns to the caller? What is the caller going to do to those arguments? It would just deallocate it, right? So all that work to exchange those things to the caller means nothing. The caller doesn't get anything back at all. Is that okay? So even though this is quote unquote a way to fix the compile time error, it's not going to do anything. Okay, it doesn't work. So the correct way to fix the problem is, to change all the PTR so that they actually dereference like that. Okay. Okay, so now we have a new task, which is to write the swap subroutine. To some of you, this is going to be a little bit boring because you got it done already. But to some of you who did not quite finish this part, this is the solution to the swap subroutine. But even if you finish your own swap subroutine, it doesn't hurt to kind of look at a potentially different solution to the same thing. So I always, draw a stack, a picture of the stack first, just to remind myself what it looks like. Okay. And then I do a CPR, CD. I'm going to, speed this up a little bit, because I want to get to the other part that I want to get to. The first thing is to decrement D to allocate for local variable T. And then now we can go into the actual C code, which is on line 14. I'm going to increment C so that it now points to PTR1, LD, BC, so that B is PTR1. But I need to dereference that one more time so that it becomes the R or the right-hand side value. So we need to do it one more time, but with B. So B is now whatever PTR1 points to. And I need to store that to local variable T, which currently is pointed to by register D because we just allocated it. So that finishes the first line of code. And then on the second line, we have to increment C so that it now points to PTR2. And then we do the LD thing again. You can see that sometimes I put in the comments because if I don't do that, I will forget what the registers are doing. B is now whatever PTR2 points to. Cool. Decrement C so that C points back to PTR1. LDAC so that A is PTR1. I don't need another LD anymore because now I have a pointer. I need to store to where the pointer is pointing to. So I need to store instead of another LD. I need to store to whatever register A is pointing to, the value of B, which is whatever PTR2 is pointing to. So that becomes, that finishes the whole operation. So PTR1, whatever it points to, is now storing whatever PTR2 is pointing to. Is that okay? So what you can notice here is there are always like double dereferencing. Double dereferencing. This is also double dereferencing. It's just that the direction is different. The first dereference is a read operation. The second dereference is a write operation. But it is still two dereferences. All right. Last one is to first retrieve whatever the stack pointer is pointing at, because that's my local variable t. So we just load that into, doesn't matter which one. Okay, A is t. And then we need ptr2, which means I have to increment c so that c points to ptr2, ldbd, oops, c. So that register B is now ptr2. Then I need to store to whatever B points to the value of register A, so that whatever ptr points to is now stored in whatever local variable t has. And that should conclude the entire program. Increment D to deallocate the local variable. If I do not do this, then the return code will attempt to use local variable t as the return address. So it will go to the wrong place in the program. So I have to do this first. Then I load. This time I can actually put it into register A, because swap does not return the value. But just as a convention, I'm just going to use register B again. Increment D to deallocate the return address, and then JMPB to jump back to the caller. So are there any questions about the swap subroutine? I kind of did it really fast, so. Is that okay? All right. Okay, so if this is okay, let me see. We got 12 minutes left. So let's go ahead and do something fun with swap. Okay, so we'll go ahead and swap in the C code the address of S1 dot, I don't know, I, and we'll exchange that with S2 dot J. Oh, okay, typo. There we go. Okay, so that's what I'm going to do. What do you think? Is it any harder than the initialization code, or is it like it's about the same? It's actually easier in a way, because when you're dealing with the initialization, not only do we have to compute the address of the member of the structure, you actually have to store into that place. When you're passing it as a parameter, and when you're passing just the address of the member, you don't have to dereference. It's actually one step simpler compared to initialization. Yes?
So you're just going to use values for D.
Hmm?
Are you just going to use values for D when you push it on the stack?
When you push it on the stack, you always use register D, because D is the stack pointer. So you just compute the address, push it on the stack, compute the address, push it on the stack, call the subroutine, undo, deallocate the parameters, and that's it. So let's go ahead and focus on this line, which is line 27 in main. And then we'll put it inside our main already partially written. So that means we can do it right here. Okay, so we'll insert a new code over here to basically call the swap subroutine. We doing okay? All right. First thing first, let's not worry about swap. Let's not worry about the first argument, because we have to push the arguments in a reverse order. So we have to figure out where is the member J of S2, and how do we find the address of that? Now this is where it looks more complicated than it has to be, than it really is, because in C, in order to specify the address of, you have to add ampersand, right? So in our mind, it seems like it is more complicated, because you need an operator to find the address of something. But when you translate that code into assembly, is it easier to get to the address of something first, or is it easier to get to the value of something? getting to the address is the first step. You have to get to the address before you get to the content. So in assembly programming, finding the address of something is actually easier because you have to do it anyway. If you want to get the value, then you need one additional dereference to get to the value. So that's a misconception that is very common because of the way we use the address of operator in C and C++. Because most of the time in high-level programming, you want the content. You want to refer to the content. But in assembly language programming, you have no choice but to get to the address first. Then you can get to the content. I just want to point it out because, just because it looks ugly in C doesn't mean that conceptually it is difficult in assembly. All right, so we need to get to S2 first, okay? So we look up the map because at this point the stack pointer is still balanced. So this picture is still true. So according to this picture, S2.j is over here. And it is 1, 2, 3, 4, 5. Is it? Yes, let me count. 1, 2, 3, 4, 5. It's 5 bytes away from where the stack pointer is pointing at. Okay, so we can go back here and just say LDI A5. Oh, we need to make a copy first. Okay. So unless you keep really good track of the register C, sometimes you can just do this again. I mean, it's not very expensive, and I don't actually think points for inefficiency. So if you don't want to mentally keep track of where C is pointing to, just reinitialize it. Okay, it's no big deal. So we want to add A to C, so that now C is the address of S2.j. Wow, that's easy. Push it on the stack. We have the second argument pushed now. The first argument needs S1.I. So if I want to just compute the difference, I can do that because I just got the address of this thing pushed on the stack, which is still in register C. The next thing I need is this guy here. So we have to subtract 1, 2, 3, 4, 5 bytes, okay, which kind of makes sense. Or I can just use register D. Oh, I cannot. Where's register D at this point? Let me point to, okay, I'm at the wrong place, so hold on a second. Let me get back here. Register D is now actually 1 byte below member I of S1 because I just pushed the second argument on the stack, okay? But register C has not moved, okay? So I can still use that approach. Register A still has 5. I can just subtract that. So that should give me back S1.I. Is that making any sense? Now, if I had any function calls between these two, then I cannot assume that register C is still having the old value. But since I have not called another subroutine yet, I can register C has not changed. So now I can push it again. Okay, decrement D, store that to the stack pointer. Now I have both arguments pushed. Now we can just push the return address. I got 5 minutes left. Return from swap decrement D. Huh? What? On line 44, it says S2.j, which is S2.j over here. This says S1.I because it is S1.I here. Okay. So we just pushed the return address on the stack, do an unconditional branch to swap the subroutine, and then the return label is here. Deallocate the arguments, and that should do it. So now we should, when this thing is all done, we should see S1.I being 3, and we should see S2.j being 4. So the 4 and the 3 should be swapped. Is that okay? All right. And I think we got just enough time to do this, assuming I didn't make any stupid mistakes somewhere. The likelihood of me actually making a mistake is pretty high. We'll see. Okay, everything looks good. No errors reported. Go to RAM file. Go to download as. And we'll call it the same thing. Just overwrite the other one. Replace. Switch back to Logic Sim. Oh, not edit. We want to reload it. So we want to load image. Same thing. And
Yeah,
ooh.
change reset because the previous. I mean, actually, I don't know if that would make much of a difference.
Well, I should reset at least the processor. And the clock is already low, so I'm actually safe now. Just by resetting the processor is fine because the clock is already low. If clock is high, then you have to turn clock low first, then reset the processor, not the other way around. Okay, so I think we're good. Control K, run the whole thing. It's all done. Let's double check. Dun dun dun. So we got a 3 here, and then we got a 4 here. So I think it is correct. Is that it? Okay, we have to refer back to the C code, and I have to find the right window. I think this is the C code. There we go. Okay, let's compare. So S1.I, which is this byte here, was a 4. Now it's a 3. And then S2.J, which is this byte here, was a 3, and now it is a 4. So the exchange actually worked, as far as I can tell. So is that okay? I mean, are we doing okay so far with trying to figure out how to get to members of a structure? So what do you think about structures? Is it a major concept change, or is it kind of like, okay, it's a nice way of doing things in C because you can package things into one thing? Well, that's why we are not writing programs in assembly. Okay, yep, go ahead.
So can you repeat for the stack pointer when you were main in that assembly code? I was looking at how the pointer for D was pointing at I. Not the pointer, but the stack pointer.
You mean pointing back to I?
The stack pointer started off at I. I was just wondering why it starts at I, not K. Because K is the last thing you push, right?
Yeah, because I initialized C back to what D was.
No, all the way up. All the way up.
All the way up. Here?
So main, like, you know how you put the stack pointer, like the notes? Yeah, how come it starts at S1.I and not S2.K? Because S2.K is the last thing you pushed, right?
No, I didn't push anything.
So
I just changed the stack pointer by 8. I just decreased it by 8.
that's it?
Yeah. Because all those bytes, in the C code, there was no initialization of the structures. So I'm just following the C code.
So if you initialize the third structure, it'll keep going.
Say that one more time.
So if you initialize the third structure, then you have, on top of S2.K, you have S3.I and then S3.
If the order is S1, S2, S3, then yes.
Okay.
All right. Any questions? Yep.
So with how the ordering is with S2 above S1,
1. Uh-huh.
if we were to declare S1 semicolon, declare S2 semicolon, would it disrupt the order?
No, it will still follow this order.
Okay.
So the idea is the compiler is assuming that we are reading from left to right, top to bottom, and it will try to preserve the ordering of the local variables in that particular order.
Okay, and then
You cannot do that in C. Because in C, you cannot intermix declaration of the variables with actual statements. But in C++, you can. So in C++, S2 in that case would have a lower address because the declaration of S2 is preceding the declaration of S1.
Okay.
Yep.
So the compiler doesn't like look ahead to find it.
No, but it does internally keep track of, how many stack bytes have been used, so it knows, where the next one is going to be. Yep. Any other questions? No questions? And you wonder, why, how GCC and G++ do not need to take aspirin or other headache medications. All right, so I'm going to go to the lab with the second or the late lab. If you guys have any questions about all this stuff, now is a good time to ask during the lab, because the assignment is due before lecture on next Tuesday.